is my pleasure to introduce Michael Liehr, who comes here from AIM Photonics, where he is the CEO. So he received his PhD from Aachen and went to work for IBM, and he had a long and very productive career with IBM, and then he describes himself as a failed retiree. So he retired from IBM and then went to SUNY Poly, where he also then became the CEO for AIM Photonics. And so I guess we'll hear about those efforts.
I was not the CEO of IBM. You know, that they teach you that on day one. Don't have that as an aspiration, right? Okay, so I will change the tone completely from the previous two presentations. I will not show any formula, and I'll stay at a very high level, but I wanted to give you an idea about the capabilities that we have and you know, what our interests are in reaching out to you folks. And by you folks, I mean pretty much everybody here in the room. So AIM Photonics is an entity that got created under the Obama administration, which means that it's not necessarily welcome with the current administration, but it has survived, and you know, since it's funded out of the Department of Defense, which is viewed positively by the current administration, we're actually doing financially okay, right? I can't say that necessarily, but those colleagues of mine that are under DOE. So these things were called NNMIs. Please don't ask me what the acronym stands for. It now has a more pronounceable name, Manufacturing USA. And what that means is that these institutes are all supposed to look at MRL 4 through 7, which is having a clear demonstration of a functional piece all the way through being able to make many of them. So it's not about basic science. So again, that's why I said it's really different from the previous two presentations. It's about taking things after an institution like yours have analyzed, made it happen the first time, and then get it to a point where it can be taken over from industry. And I have a few charts that talk to that. And the other thing is AIM Photonics, again, is integrated photonics. So I always have to explain that we're not just doing everything in photonics, because it's a very broad industry. We're putting stuff on a wafer, hence these beautiful pictures in the back. And by the way, we paid IEEE to create this marketing material, so I feel compelled to have to show it, not just... Okay, so the question is, how do I get this thing to advance? Apparently it's not as easy as I thought. Okay, there we go. So first of all, let me talk about applications. And Carl, it was nice to say that in quantum computing it's hard to see what the applications are in the foreseeable future. Here, AIM Photonics, because of the proximity to manufacturing, is of course looking at market segments and then tries to determine what kind of technology we are to develop that is appropriate for these market segments. And I realized that you can't really see these things particularly well, but the four market segments that we're focusing on are datacom and telecom. That's the only segment that in my lifetime is going to have significant enough volumes. Right, so today we're talking about transceivers, we're talking about data centers, and replacing the cabling in data centers by fibers, which will decrease the power consumption in these things substantially. And in case you missed it, the nation at the moment spends about 2% of its entire electrical bill on data centers like the Amazons and so on. Right? So this is an important thing that will extend the life of these, or at least makes them more powerful as we go along. The next one would be RF analog. I mean, I'm sort of euphemistically putting 5G here. My personal opinion is less likely that that's going to make it from a photonics perspective. But that segment also has a lot of interest for my sponsors. And again, similar applications, if you're flying an F-35, there's a lot of cabling in there, in this case RF cables, they're heavy. If you can replace them with a fiber, you gain advantage in terms of weight. They care about stuff like this, and of course we're happy to help them with that. These two segments here are much more volume than any of the previous two will likely have. Now, a few 5G excluded, but the problem with both of them is that they're not tomorrow, right? I mean, in particular, when it comes to PIC sensors, I mean, infinite number of applications, and that comes, unfortunately, with an infinite number of solutions. So there's no common platform that's emerging for these things. We're talking simple things like, what wavelength range are you into, which for integrated photonics means a huge deal. Whether it's in the liquid or in the gas phase, application space is very, very widely dispersed. We actually built one with the University of Rochester to detect sarin. You might imagine what that could be used for. But there are certain things that you absolutely can do, and the sensitivity and the cost point of these is very interesting, and the cost point would drive a very large volume. But the problem is standardization in this space is nowhere. And then pick away, think of that as LiDAR. And again, the whole idea would here to be a non-moving part, so a phased array that scans the beam independently of any mirrors or anything like that. Again, to get the price point to the point where the gizmo on the top of the car is not more expensive than the car itself. Right? So those are the things that we're looking at, and in keeping with a more industrial orientation, we have an organization that's like you find in a lot of large industries. It's a matrix organization. These are the customer segments in that sense, and here are the manufacturing technology, so I'll focus most of what I say from here on these manufacturing segments. Okay, so what is integrated photonics, or what's included in the manufacturing ecosystem? It's really four things. The first one is, you need to design these circuits. I'm probably saying the wrong thing here to this audience, but we really don't want people to start, solving Maxwell's equation before they do these. If you look at what the electronics industry does, they have created this hierarchical system that hides all that complexity from the designer, so you can have somebody who has a bachelor's degree get on the screen and design a chip, even a complex chip. That's what is necessary in order to make this stuff pervasive. As long as it's limited to PhDs, there just aren't enough of them to do, this kind of job that, for a largely, large volume industry that would be needed. So we want to dumb this system down in a sense, and basically we do that by building a hierarchy in the design where the designer really doesn't have to know what goes on the fab floor, and where you create preconceived blocks of IP that they can just reuse. It's all time to market, and it's all simplicity and facility to make these things happen. So we have a significant effort in that, as you might imagine, and it's really at this point still an uphill battle. This industry in general feels a little bit like the semiconductor industry in the 70s, early 80s, when none of these concepts in the semiconductor industry were embraced, where people thought they gained an advantage by rolling their own. Nowadays nobody does that anymore. So it's going to take a while before the industry embraces these concepts, but we feel that it's partially our job to push that and make sure that they do. Of course, the next thing here is you have to have a wafer-based foundry. That's me, in case you were wondering. Again, that's one of the topics that maybe after my talk I'm more than happy to talk to you about. We do this in silicon and indium phosphide, but I have to be a bit careful about the indium phosphide component because that's a commercial activity, so it's with a company, so it's a lot more restrictive, as you can imagine, whereas we are a fairly open facility. You need to test and package this stuff. I'll speak more to that. That's where most of the cost of one PIC assembly is. So it's really important that these two pieces here, the connection to the outside world if you need it, of course, and the packaging and test, are the two areas that we're focusing on a lot. So I spoke to that a little bit at the moment. I'm sort of happy to report that we've been around for roughly, say, call it almost 3 years now. And over the course of those 3 years, we've made quite a bit of progress with the large electronic design automation companies. And we're talking about the Cadences, the Synopsys, and the Mentors of the world. It's interesting to watch that they do what they usually like to do best. Smaller companies like Phoenix Software had a fairly compelling offering in terms of layout and simulation tools. And Synopsys just acquired them. I guess that's how that goes. So in principle, we're focusing on the three big guys and then working with them. And while I make a fairly strong statement here that no such system exists at the moment, we're making great strides towards it. And all three companies, Mentor, Synopsys, and Cadence in particular, are paying attention and working with us. So that members of IM, we have various classes of members. There are tier 1 members, which is the top category. And we're, as I said, communicating and working with these guys all the time. It's also a very international effort, by the way. Phoenix, for example, was a Dutch company. Again, they're now part of Synopsys. Okay, so question number one that we typically get asked, what substrate? So there are two choices really at the moment. Either you can do silicon or you can do indium phosphide, and the question is, what do you use for which? There's a fairly stark difference in terms of price. There's also a fairly stark difference in, the sensitivity of the substrate, both to mechanical pressure, to defects, and so on. Silicon usually wins hands down, right? Now, the problem with silicon, as you guys all know, it's not exactly optically active, so here's the real problem, right? But fundamentally, if you can put it on silicon, it'll be a winning proposal. Now, indium phosphide is definitely a capable material system, don't get me wrong. And to first order, since you have already lasing capability built into the substrate, amplification built into the substrate, today there are certainly solutions that indium phosphide will win on. Again, our goal is to, in a sense, keep that niche small and mostly towards the high end. Now, also indium phosphide from a semiconductor, and this is more like the electronic piece of it, speaking, is much faster than silicon will be. So there will always be applications where people want to be a generation or two ahead in terms of performance, speed, or whatever it may be, and they will stay with indium phosphide. But not unlike what happened in the semiconductor industry, where you can either think of using gallium arsenide or maybe germanium-based systems. They are confined to a niche, and the vast majority of things are built with plain silicon. So, as I said, issues remaining the small size and the cost of these wafers. I mean, again, just for reference, a silicon wafer, 300 millimeter silicon wafer, plain silicon, admittedly, is about $70. A 3.5 indium phosphide wafer, 3 or 4 inch, is about 800. I mean, that alone is a huge disadvantage if you're building something on 3.5s. Now, the goal would be, what can we do to put these active components on silicon in order to bring the cost down? And that's really what manufacturing is all about. So here's a bit about us, and it's really a very condensed version of what we are. So SUNY Poly is the university that is supporting AIM. So my clean rooms are supporting, a portion of my clean room supports the AIM wafer fabrication. And in simple terms, I mean, we have two kinds. This is actually on a small section of the total. We have a total of 135,000 square feet of clean room, class 1 compatible clean room. This here is only like 12,000 of the total. I put it here for completeness. We're using it for silicon carbide manufacturing, so 6-inch wafers. The rest of the facility is 300 millimeter. So we have the capability to build a complete chip and then some, and I'll get to and then some statement in a second. So use the size. This is used today to do CMOS development primarily, so 5 nanometer at the moment, for those of you who are familiar with the generations of these. We, SUNY Poly, were part of it up to 7 nanometer. The club of those companies that can still afford 5 nanometer, even from a design or use perspective, is very small by now, single digits basically. And as I said, it is used by AIM as a foundry. And so one of the things that we were charged to do by the Department of Defense as part of this program was to make or provide a path for small companies, universities, and of course the federal government to access this capability. So we spent the first, call it, couple of years or so of our existence in putting a capability in place that should allow a relatively inexpensive path into using this. So what this is called is the multi-project wafer. The concept is fairly simple. I mean, you have a mass set that can be, $100, $200, $300,000, which most faculty support don't reach that far. So you subdivide this thing. We have up to 12 customers on each of these, and one of those tiles is even subdivided further. So you can buy a tile basically on this for a relatively modest amount, between 30 and 100K. This includes the wafers that go with it. Since these are 300 millimeter wafers, you get quite a number of die out of it, and as you can imagine, we're not starting just a single wafer, so you get plenty of die typically. We are hedging against yield losses, so I start more wafers than I typically would need. Again, one of our projects is integrating 3.5 lasers. The other thing that I'll mention towards the end, we do 2.5D and 3D integration. 2.5D is if you attach a die to a wafer. 3D is if you slap two wafers together. We do both. One of those, actually, the 3D is in a commercial application with a customer that doesn't allow me to use his name, but it's a fairly large company. Concepts like this can be used to create superconducting cavities by just moving to wafers that have, say, aluminum on them. So you get the implication this is not just good for photonics, but it could be used for other things as well. We do have integrated inline and optical tests, inline being the electrical, and optical obviously being checking up on what you're building while you're building it, because it does take 3 months or so for stuff to go through the line. You don't want to screw it up the day before it gets shipped, right? And then we do have in-house packaging and assembly. So a little bit about, what does it take to put a simple transceiver together? Simple, is sort of in real quotes, right? So you need to first order 2 different wafers. An integrated photonics assembly, a PIC, typically does not include the CMOS portion. I mean, if you're trying to include it, the companies who do that, you just drive up the price of your PICs tremendously. The CMOS generations that are used for these today are sort of in the 14 nanometer range, so it's pretty expensive, as you can imagine. Photonic features are large. Now you multiply the area that these features take with the price point of these highly expensive CMOS wafers, and we can argue whether that makes sense or not, right? As I said, there are people who believe in it. I tend not to be, and as a consortium, it's also not the right approach because you tie yourself to a particular foundry. The second one is a Photonic Ic. That's the stuff we build, so you need one of each. Typically, they're not the same size, so you do a 2.5D sort of an assembly. You put the whole thing as a stack onto a carrier. The carrier is there to help mitigate against the thermal expansion mismatch with a laminate that this eventually goes onto. Eventually, you attach a laser attachment. This is a finished small laser. We're talking tiny little things, right? You can see a picture of one of these right there while it's being assembled. This is an assembly problem, right? So what I mean by that is that the placement accuracy, because from an alignment perspective, you basically have at least 3 axes, maybe more to worry about, and it goes into a tiny waveguide. So the placement accuracy is 1,000 angstroms or better, and these tools just can't do that, right? So there's typically what you can buy for a reasonable amount of money is about 1 to 3 micron placement accuracy. So it is a real problem that needs to be solved. How do I overcome that order of magnitude? And there are a bunch of tricks that people are playing, but I'm not portraying it as being something that people have solved at the moment in a financially or economically viable way. The next thing, it goes onto a laminate, and then on the laminate you attach the fiber, and that's the next problem, right? So the problem there is just the same. The fiber diameter is typically 120 micron. It goes onto or connects to a waveguide that's 2,000 angstroms. The placement accuracy is the same problem. Now you get this bulky thing that has a big tail on it that also levers. It is an assembly problem. It's a stability problem. It's a reliability problem. So at the end of the day, 2 of these things are cost. Actually, the top one is also, because if you do that wrong, then you got a dead die on one of the others, so you just kill 2. All of these are cost problems, but all of them are fairly serious, and those are the sort of things that we are trying to focus on. Again, that's what I mean by manufacturing. Fiber attach and laser attach being the 2 biggest one of those. Okay, so these were assembly and packaging problems, right? So what we're doing here, and to support this, we have started building or re-equipping a facility in Rochester, and so we have the Wafer facility in Albany. Here we have a test assembly and packaging facility. This is in the Kodak Business Park. onsemi really owns the building, but we are leasing 2 floors of it, converting it into a clean room. The clean room is a lot smaller than what we have in Albany. It's about 12,000, maybe 13,000 square feet. The area we're covering there altogether is more like 35,000 square feet. And within the clean room, you have the capability there that you can read faster than I can talk to, so I'm not going to go into the details. The whole point of this is the wafers will get finished up to a certain point in Albany. Then they get shipped to Rochester, where we put the back-end metallurgy on it, and the back-end means the stuff that is needed to put a ball, like in a ball-grade array, onto the wafer or onto the interposer. sort of the picture you see there on the top, and then this thing gets attached to a laminate. So we're doing all those steps, the singulation, the balls, as well as the testing in this, or will be doing that in this facility in Rochester. And again, this statement there in red is a key. The semiconductor industry, the ratio of the cost of a package compared to the cost of a silicon wafer is about 25 to 30% in the package. Because a silicon wafer, especially in advanced CMOS, is extremely expensive. Here it's the opposite, right? So we really need to focus on this, and again, it requires innovation, right? I mean, there are things that how can you avoid the cost of an active alignment, and the word active means, think rows of elderly ladies, assembling these things, measuring them, typically in a place with low cost labor, right? And if we want to compete in the U.S., that has to be eliminated. Somehow you need to have people out of this system and automate it, ideally not even in an active alignment, but in a passive alignment scenario. Okay, so there are some concepts here that we're working with our colleagues, in this case here, Arizona, with where the idea is to take a laminate and then apply a thin sheet of glass to it, with a collaborator that sits in the room here, and then with the idea, of course, to get the waveguides defined differently, lithographically, rather than mechanically attached. So the same concept, or in principle, similar idea, is what we're intending to do on the laser side. As I said, attaching the laser is a problem because you need to know it's a good laser. The mechanical assembly is difficult at best. If you do this with the next step, so I should step back on the transceiver business. Today, what you can start to buy are 100G transceivers. The next generation, whether that's 400 or 800G, will no longer be able to do with a single wavelength. These 100G are single wavelength transceivers. You probably need 4, 8 or more, and that implies that you need 4, 8 or more lasers. The problem of placing a single one just got so much harder and so much more expensive that that's just not a viable path as it's been done today. So our solution to this is that we would like to grow the lasers directly on silicon. Now, without going into much detail, because AIM is a member institution, so you have to be a member to be eligible to get the details here. Growing quantum dot lasers on silicon has become a lot more possible. A lot of research has been going on, and one of our key collaborators in UCSB, John Bowers, has really gotten this process to a point where we now feel that it can be brought onto a 300 millimeter wafer basis. The primary one that's, I think, the easiest to understand, and the largest mismatch between indium phosphide and silicon is fairly large. So you get misfit dislocations, those kill a laser, especially if it's quantum well laser. By doing quantum dots, several thousand it is for a single laser, you pretty much eliminate that problem because you kill maybe a handful of these things you barely notice. There's a bunch of other things that come with this. Another one that is actually fairly significant, lasers have stability problems because there's reflections. I mean, once you emit the laser light into a waveguide, typically the reflections, they create instability in the laser. These devices are a lot less sensitive towards this, so we can eliminate one of the key problems in the assembly. Typically, people have to put an isolator there. That's a bulky little thing that's expensive. I think we can probably do away with the isolators by having integrated indium phosphide quantum dot lasers. So we're embarking on this. Actually, we've, as you might imagine, spent quite a bit of it already. One of the remaining issues is reliability of these things. And there too, I wouldn't be saying it, we have made tremendous progress over the last, call it year and a half. And John's lasers today actually look like they are now in the range of where it becomes industrially interesting. So how do we work? And I, again, have removed the names of the guilty here because I'm not allowed to. This is one of those interesting things when you get engaged with industry. It comes with a whole bunch of constraints, among others, them telling you that we won't say anything until there's a product out there. You don't want to pre-announce anything, stuff like that. Right? So that's part of the things you have to accept when you want to work productively with industry. But This goes back to the concept that I talked about at the very beginning. University research, almost by definition, goes here in this first range of MRL 1 and 2, maybe into MRL 3, and industry research or activities really start when it's volume, right? There's a gap in between. There's different names for this thing, valley of death or whatever you want to call this thing. That all these NMMIs or manufacturing USA institutes were created to fill this gap. By the way, the concept is taken from the Fraunhofers. It's probably the closest equivalent to what we're trying to do here in the US. So this is where AIM sits, and this is where SUNY Poly, as the foundry behind AIM, sits as well. So we're taking ideas and concepts once they've reached a certain level of maturity and bringing it into our facility, and then ultimately, because we're not a high volume capability, we're taking this and then transferring it to industry. And the same problem on that side, by the way. If you talk to, say, a Global Foundries, a friendly neighborhood foundry near us, and you say, well, I am a customer, I would like 100 wafers. Now, for most of you, that's an outrageous number, but the guy is going to throw you out. Right? It's simply because, A, you're asking me to come up with a process that's different from what I'm running today. You don't promise any reasonable volume. Why would I actually entertain? Please go. Okay, so our role here is, and usually it's not that friendly. Right? So our role here is that we need to be able to take this to a point where a customer of ours has a demand of several thousand wafers, and then it starts to be interesting to a foundry. So we have examples of this, but again, I'm sorry I can't tell you who it is, but to be announced is probably the best I can say. We have two, one for the wafer and one for the package. And again, you see the universities we're working with, and again, after my presentation, I'm more than happy to talk to all of you about how we can engage here. So this is sort of what SUNY Poly does. Given that I'm running a little short here, I'm going to be very quick. Again, we do support customers with various service offerings, including design help, because a lot of people apparently need it. And we have a number of partners in crime that we're working with. This is a chart I can skip very quickly. We do have ISO certification now. Again, that's far from most of your thoughts. It's important for what I'm trying to do. And believe me, in an environment like ours, that was a fairly heroic effort. We also have AIM Academy, so there's educational collateral that's being developed. The intent is also to train folks either from industry or grad students, obviously, to have a qualified workforce. This is a real problem in two areas. It's in test and in design. There are just not enough of them, right? So we have an active program to help that along. So I have two more charts just to touch on something to sort of whet your appetite. They are not AIM activities. They are activities that are in the photonic space. They're a lot more tentative than what we're doing with AIM, with the previous. But I wanted to put it out there because we're clearly interested in. We believe that photonics in particular can make a difference. One of it is call it neuromorphic computing. I think you can build a neural net based on photonic devices. The main problem, as you imagine, there's no amplification. So having the capability of providing amplification in this would help a lot. Hence the quantum dot laser making, in all likelihood, in my opinion, a big difference here. Now this is a few years down the road, right? So the previous stuff is sort of between 1 and 3 years. This is 5 and more. And the next one is even further out. I probably get violent agreement from the previous two speakers. If we get a quantum computer that really is capable of doing something, we're 10 years or more out before you have something, and I don't have any expectation that it will be in the form of a laptop in my lifetime. But the goal again would be to see what we can do with integrating photonics with either superconducting or other solid-state material systems, knowing that some of those things that were mentioned earlier today, like diamond, are obviously not compatible today with our platform. So it is probably an active dialogue to see what material systems are compatible and see whether they fit in some shape or form with the research that goes on here. And that's again what I'm doing with universities like UCSB, for example. We're not just waiting for something to be developed, we actively talk together about how it needs to be developed for us to be able to take it quickly. Right? That's the key. Okay, and then last not least, none of this happens without the right people. Two previous speakers also, had children. So we have this cast of characters that, we've been basically living with for the last, 2.5, 3 years. So I want to acknowledge their contribution, as you might imagine. And with that, I'm done.
All right, questions?
Yes.
Yes, you are basically merging like your optics to in the semiconductors. Right?
Yes.
So I'm wondering, you generate some laser source. Is there a need for some optical component like polarizer, beam splitter, or mirror in micrometer scale?
The simple answer is yes. That's part of our component library. So we typically have, you can design anything you want to as long as it's compatible with our ground rules. So we offer access to our facility through the MPW program without a component library. There's a lot of folks who like to design their own. Right? In my opinion, it's not very efficient if somebody has done it already and spent money and energy to develop something. So we have a component library that has prefabricated things like splitters, polarizers, detectors, waveguides, you name it. There's a list of about 40 elements that we're supporting, and we're adding to it as we go along. The thing we need mostly from users is what is really needed, because the library is based on the know-how and expertise of the folks that you saw on the previous page, but I'm not saying that that's exhaustive by any means. But we need some level of statistics of which elements are reused by folks and what is missing, so we can complement our library offering. But yes, they're available, they're part of our technology offering. You just have to download our design kit to get them.
Thank you.
Okay, any other questions? Yes.
Thank you for a nice overview. About 10 years ago, Intel was also in the game with the optical components of silicon. Have they stepped out, or are they still involved?
Oh, they are absolutely active.
Okay.
I don't want to get it on record of what the discussions with Intel have been, but they have chosen at the moment not to be a member. Interestingly enough, there were two of the whatever we would call founding members, but then at the end of the day, they decided, primarily for IP reasons, not to participate. If you are a consortium, there are certain rules that need to be obeyed that relate to IP, especially when programs are funded by the federal government. The federal government has march-on rights, and university faculty that come with IP have rights to that IP as well. And there are certain companies that don't like that.
Their role was primarily in the datacom, telecom, or was it in analog RF?
Both.
Both.
Okay, with that, let's thank our speaker.